Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chennapgood. Dear students, in the previous class we discussed about what is conduction heat transfer and what is Fourier's law of conduction, and we have solved one numerical on conduction heat transfer. Dear students, come we'll move to our next topic. So the next topic is thermal conductivity. What is thermal conductivity? Thermal conductivity of material is defined as the quantity of heat energy that flows across the opposite faces of a cube of unit length in 1 second, when the opposite faces of the cube are maintained at a temperature difference of 1 degree Celsius or 1 Kelvin. Dear students, what is this thermal conductivity? Dear students, to understand that, what I will do, I will try to take in a metal plate here now. So I will take in a metal plate. Okay, so that is a metal plate. Okay, then what I will do, dear students, I will try to pass the heat at this face. Then what will happen? The heat is going to pass across the metal plate. That means what? Heat is going to cross the metal plate. So the amount of heat supplied I will mark here as a Q. Okay, then the area of the metal plate I will mark here as a. Then thermal conductivity of the material I will mark here as a K, dear students. Okay, so now heat is going to transfer from phase 1 to phase 2, or phase A to phase B we can call. The temperature at point 1 or phase 1 I will mark here as a T1. The temperature at phase 2 I will mark here as a T2. That is nothing but what? Phase 1 and phase 2 of metal plate. Then now heat you are going to transfer in this way, right? When you are going to transfer heat, right, there is some resistance in the metal plate. That resistance we can mark here as a R. So initial temperature is T1 and final temperature I will mark here as a T2. The resistance which is offered in the flow of heat direction I will mark here as a R. The same thing I will show it in a circuit. That circuit we can call it as a thermal circuit, dear students. That thermal circuit you can see here now. So initial the temperature of the metal plate is T1, then final temperature of the metal plate is T2, then there is a resistance in the flow of heat. That resistance is represented like this. Then the resistance is represented as a capital R, where capital R is equal to L divided by K into A. The direction of heat, that is heat is moving from T1 to T2, so I will mark here as a Q, dear students. Okay, now so what I will do to understand better, what I will do, I will assume this is my front view, then I will try to draw the diagram for this particular point 1, so that you can see here, dear students. Now, so now what I told, the heat energy is supplied at one phase. So that phase I will mark it as a phase A you can call, or phase 1 you can call, dear students. You can call it as a phase A and you can call it as a phase B. So you can call it as phase 1 and phase B, or phase 1 and phase 2, or phase A or phase B. So the temperature at phase 1 that I will mark here as T1. The temperature at phase 2 is T2. The heat is moving in this direction. Heat is moving from high temperature region to low temperature region. When that heat is moving, right, there is some resistance. That resistance we can mark here as a R actually, dear students. Then that metal plate having a thickness, that thickness I will mark here as a L, dear students. Then if it's so, there is a Q, there is a L, and there is a change in temperature. When it is a T1 and T2, right, there is a change in temperature, that I will mark here as a delta T. Then what is thermal conductivity? Thermal conductivity in simple terms I can explain, I can define as it's a property of a material and it is have an ability to conduct the heat. Thermal conductivity is a property of a material. It is nothing but what? Ability of material to conduct the heat. That too per unit length, per unit time, then per unit degree Celsius temperature difference. If how much amount of heat is going to transfer in that particular material for 1 meter length thickness, then 1 degree Celsius or 1 Kelvin change in temperature, one thing, and that too for unit time, that is known to be thermal conductivity. What is thermal conductivity? That you can see here now. We know the unit, right? So dear students, thermal conductivity I can see here now. It is what? Watt per meter degree Celsius or Kelvin. What is thermal conductivity, dear students? Thermal conductivity I can define in simple way. The amount of heat transfer, it is a property of a material, and it is the ability of material to conduct the heat. That is to that too for per unit. How much amount of heat is going to transfer per unit time, per unit time. So for unit time, okay, for unit time, that is equal to 1 second, I can say. Example, for unit length, that L equal to, I can here it is 1 meter. Then for degree change in temperature difference, that difference how much it will be? It will be 1 degree Celsius or 1 Kelvin. So that means what, dear students, you can see now, through 1 meter length and delta T is 1 degree Celsius or 1 Kelvin, and per second how much amount of heat is going to transfer. That is nothing but what? Thermal conductivity. What is thermal conductivity? It's a property of a material, and it's an ability of a material to conduct the heat per unit length, per unit change in temperature difference, that too for unit time. That property we can call it as a thermal conductivity, dear students. Okay, then that thermal conductivity we can calculate with the help of Fourier's conduction equation. What is that Fourier's conduction equation? That you can see here, dear students. What is that? So we know already Fourier's conduction equation. What is that? Q is equal to minus K into dt by dx. Some authors, as I told, dear students, some authors they will take thickness of the metal plate L or T. Some authors they will take L or T, or some authors they will take dx. It's up to you. But here what I will do, I will take it dx. So Q is equal to minus K into dt by dx is there, right? So here is the K value. I will try to take the K value. I will do small changes or small modifications in the equation, or I can rearrange this equation, and then I will try to take the value of K. So therefore K is equal to then Q divided by this. I will take it this side. So Q divided by A. Then it will go to the left hand numerator side, dx. Then it will come dt. It is capital dt. That means what? Q divided by that means what? I can calculate the thermal conductivity, that is K, by using Fourier's law of conduction equation. That is K is equal to capital Q divided by A into dx by dt. So that is nothing but what? Watt per meter Kelvin. How it is watt per meter Kelvin, dear students? You can see here now. What is the unit for this? 1 minute. Okay, so what is the unit for watt? Q, that is watt. Okay, what is the unit for area? That is meter square into what is dx? That is thickness or length of the plate. So that is will be in terms of meter. Then what is change in temperature? Either it may be in degree Celsius or it is in Kelvin. So what I can do, dear students, here I will cancel meter square and meter square. Then only watt is left out at the numerator side. Then what I can do now? Watt per, here 1 meter is there, meter degree Celsius, or you can take it Kelvin. That means what? Thermal conductivity is nothing but what? Amount of heat transfer for unit length, that too for unit degree Celsius temperature for unit time. That is known to be thermal conductivity, and the thermal conductivity we can calculate with the help of Fourier's law of conduction equation. So that equation I will write it here, dear students, now. So what is this? You can see here now. Okay, so thermal conductivity is represented as a K. K is equal to what? Q by A into dx by dt. Unit watt per meter Kelvin or meter degree Celsius, where Q is what here, dear students? Is the energy conducted, and A is the area, then dx is the thickness. Q is what? Watt actually. Then area is the meter square. The next dx will be the meter. Then dt is change in temperature, either it may be in degree Celsius or it is in Kelvin. So this equation I can write like this also. K is equal to what? Q divided by Q into L. L is nothing but what? Thickness, divided by A into delta T. Then the dimensions for thermal conductivity is ml T to the power of minus 3 K to the power of minus 1, dear students. This is the equation we can use to calculate the thermal conductivity of any given material when there is a conduction heat transfer. Okay, now classification of substance based on the thermal conductivity. Based upon this thermal conductivity, we are going to have two important classification of substance. One is good conductors of heat. What is good conductors of heat? These substances have large values of thermal conductivity. So the materials or substance which have more thermal conductivity, those who will call as a good conductors of heat, or good conductors of heat, or good thermal conductors, we can say. Most of the things, all metals are the good thermal conductors. Why so? Because they are having more thermal conductivity. Because of that, what we can say, those substance we can call it as a good thermal conductors. So for ideal conductors, thermal conductivity, that is K is equal to infinity. It's ideal. Practically it is not possible, dear students. For ideally, what we can say, the thermal conductivity of material is equal to infinity. It is for what? Good conductors. Second classification of substance is bad conductors of heat or bad thermal conductors, we can say. What are these substances are? What are these bad thermal conductors? That means what? They are having small or very less thermal conductivity. Those materials we will call it as a bad conductors of heat or bad thermal conductors. Example for bad thermal conductors we can give wood, air, wool or etc. Then thermal conductivity for ideal bad conductors is, that is K is equal to 0. But dear students, we can take air or wood, whatever it may be, it is having some 0.0 something else, but it is very less thermal conductivity it is going to have. But for ideal case, what we will do, we will assume that K is equal to 0 for the bad conductors. Okay, this is about classification of substance based on the thermal conductivity. Next, there are some factors they are going to affect on the thermal conductivity. What are the factors now? You can see here now. Some factors are there. They are going to influence the thermal conductivity. What are those? You can see here now. First one, material type. Dear students, what I have taken? I have taken in a burner here. Okay, I am going heat to the spoon, metal spoon. It is cold and it is going to heat it. I am going to pour the oil. Then heat is going to transfer from this end to this end. Then heat is going to transfer from this end to this end, dear students. If the spoon is made up of metal, then what we can say, it is having high thermal conductivity. Hence what we can say, more heat transfer is going to takes place. That is a one influencing factor for the thermal conductivity. That is what, if it is a metal, it is having high thermal conductivity. Hence we can get more conduction, heat transfer. If it is made up of non-metal, or you can take a wood or gas, anything else, any materials, they are having less thermal conductivity. Hence what will happen, there is a less heat transfer. That is a first type. Then material also play an important role in the thermal conductivity. If it is metal, more thermal conductivity. If it is non-metal, less thermal conductivity. Then temperature. Second influencing factor for thermal conductivity is temperature. If the more temperature is here, if it is more temperature at this point, heat is going to transfer from this end to this end, right? If there is more heat transfer, then what we can get? We can get more thermal conductivity. If we are getting more thermal conductivity, then more rate of heat transfer we can achieve. One thing. Next, density. Higher denser materials have more thermal conductivity. Like you can take a copper, steel, okay, cast iron, like that we can take. Compared to non-metals, they are having high density, hence they can transfer more heat and they have more thermal conductivity. Then moisture content. So moisture content, if it is a material, right, assume that it's a material, you can take aluminum or something else. If it is having some porosity, then what happens? There is a small air gap we are going to get. If it's so, then what happens? We are going to get less thermal conductivity. Those materials which are having moisture content in it, they are going to have some air voids or moistures in it, right? They are going to cause the less heat transfer. Why so? Because they are going to have less thermal conductivity. Hence moisture content, if there is more moisture content, less thermal conductivity. Then impurities. If the metal plate is there at aluminum, you can take, if there is more impurities in the aluminum spoon or any metal spoon, then what happens? Those spoons, they are going to have a less thermal conductivity. Why so? There will be a thermal resistance. That means what? If there is a more impurities, there will be resistance to the flow of heat. If there is a resistance of the flow of heat, then what happens? There is a less thermal conductivity. So that is also one of the important factors which is going to affect on the thermal conductivity. Dear students, we can see here now. Then what all the materials they are having thermal conductivity? So you can see here now, copper having 400 watt per meter Kelvin. That means what, dear students? 400 watt heat transfer is going to happen per meter, that too per degree Kelvin temperature difference per unit time. That is copper having thermal conductivity of 400 watt per meter Kelvin. Then aluminum, that means what we can say? Copper is the best thermal conductors or thermal conduction of heat. Aluminum is going to have 200 watt per meter Kelvin. Okay, next here it is 200. Some authors they will represent they will show 205, 210. It's okay. 200 watt per meter Kelvin. The next steel having 50 watt per meter Kelvin. Then water having 0.6 watt per meter Kelvin. Dear students, you can see copper and water. There is a lot of difference. Even it is not 0.1%. Even not 1%. We can't compare with this now. It is 0.6. Water having thermal conductivity of 0.6, whereas copper having 400 watt per meter Kelvin. So for that purpose, wherever the heating application is there, right, we are using copper. The next air. Air, you can see air is too less. That is 0.026 watt per meter Kelvin. Almost it is 0, we can say. Then wood 0.1 to 0.2 watt per meter Kelvin. Then some insulation materials that you can take wool or some insulation materials, they are having 0.03 to 0.05 watt per meter Kelvin, dear students. Okay, now, so these are factors influencing the thermal conductivity. Material composition. If material composition, that material, if it is having strong interatomic bonds, then it is going to have more thermal conductivity. Then if the structures, if it is well organized, then that material is going to have more thermal conductivity. Then temperature. If it is the materials, if there is a more temperature, then what happens? The rate of heat transfer will be more. How it's so? Because thermal conductivity will be more. Then density, that we already discussed, and depends upon the phases of the material. If it is solid, more thermal conductivity. Liquid lesser than solid, then gas is very, very less. And thermal conductivity between solid and liquid and gas, there is a lot of difference, dear students. Okay, so now microstructure, grain size, it depends upon grain boundary, porosity. These all influence the thermal conductivity, dear students. So here are some values for thermal conductivity. Yes, copper, what I told, dear students, 399 watt per meter Kelvin or 400 watt per meter Kelvin. Aluminum 200 or 237 watt per meter Kelvin. Like that, you can take carbon steel, you can take a glass, plastic, water, ethylene glycol, engine oil. These all are what? Thermal conductivity for the different fluids and materials, dear students. Then how to determine the thermal conductivity? To determine that thermal conductivity, we can have a small experiment, dear students, now. So I will take an insulation, then I will put insulation here also, at the one side of the insulation. What I will do here now, I am going to put an electrical coil. So then what I am going to do, I am going to supply electricity to this, then coil is going to get heated. Then this is a metal plate, sample material I can take, or sample metal I will take it. Then that metal is surrounded by insulation in all sides. Then what happens now, when I am going to switch on the electrical heater, right, then what happens, it is going to heat, then it become high temperature region. So that temperature region I will mark here as a temperature T1. The heat is going to transfer from high temperature region to low temperature region. The temperature at low temperature side I will mark here as a T2. Temperature at high side I will mark here as a T1. The heat is going to transfer from high temperature region to low temperature region. Whereas the thickness of the sample material I will mark here as a L. So then K I will take it as a thermal conductivity notation, dear students. Now with the help of this data, what I will do, dear students, I will switch on the electrical heater, then it will get heated, this become high temperature region, that is T1 I can take. I will take the reading of T1, then I will take the reading of T2, then I will measure the thickness of the sample material or metal, you can say. With the help of this data, what I can do, I can calculate the thermal conductivity. How? Again, Fourier's law of equation. So what is that? That is K is equal to L into Q divided by A into T1 minus T2. What is L? Thickness of the material. Then what is area? The area of the metal plate. Area of the metal plate, that too perpendicular to the direction of heat flow. Then divided by what? High temperature region minus low temperature region. Then Q. What is Q? With the help of Q I can calculate voltage and current. So when we are going to multiply voltage with current, right, we are going to get heat, that is watt. So that I will substitute here. Then I will do simplification. I am going to get one value that will be in terms of watt per meter degree Celsius, or it is in Kelvin. That value we can call it as a thermal conductivity. So thermal conductivity I can determine for any solid materials by using this experimental setup. This is about thermal conductivity. Dear students, we'll continue next class. Thank you. If you really like my videos, please do subscribe, comment and share to your friends. Thank you.